Last lesson of exponents and logs. This is the good part. Simple log equations we're going to solve, and complex log equations. And now finally we get to do growth decay questions algebraically. The questions on your quiz that you could only solve y1, y2 intersect on your calculator, we can now solve algebraically using logs. So let's get started. A couple of warm-up questions that aren't involving solving using logs, but let's find log base 2 of 4x. So what we can do here is, using the information given, is switch this to exponential in order to solve for the missing value of x. So we have x is equal to 8, and now we can use x is equal to 8 in the second part of this problem. Log base 2 of 4 times 8. Well, log base 2 of 4 times 8 is log base 2 of 32. And we know 32 is a power of 2. 2 to the 5 is 32. So this is equal to 5. Now this number 2 is a great question. This is also on the handout with the diploma questions. So excellent question because it involves your laws of exponents and your laws of logs. Looks kind of scary to begin with, but if we take our time and work through the laws of exponents first. So laws of exponents means we keep the base the same and add our exponents. This is multiplying with the same base. I'm going to leave the denominator alone for now. All right, now log base 6 of, we're adding our exponents. When we're multiplying with the same base, the law of exponents tells us to add our exponents. Well, when I add these two logs, I can put those two together as a product. So I'm going to, the easiest way to continue this, down here, write this as square root of 2, as a single log, log base 6, 27 times 60. 432. Okay, I'm not going to worry about evaluating that right now. But what we are doing is now dividing with the same base. Well, we know when we're dividing with the same base, we would subtract our exponents. So if we subtract these two logs, so we keep our base the same and subtract these two logs. Log base 6, 432. And now we use our law of logs. We're subtracting, so we can write this as a single log, log base 6. So when we do 432 divided by 12, we get 36. And what a nice number that is. Log base 6 of 36 equals 2. 6 to the power of 2 is 36. So after all that, we end up with root 2 squared. Square root of 2 squared is just 2. All right, it all works out to 2. Pretty cool question, don't you agree? I hope so. All right, I'm going to pass this question and go right to this, or pass that slide and go right to the solving equations. This is the good part. Now, every time you were asked to solve an equation up to this point in your math life is you are allowed to do anything to an equation as long as you do both sides. You're keeping a balance on both sides of the equation. And this also applies to logs. So we are going to be allowed to put log on both sides of the equation. And we're going to use log base 10, which means we don't have to change the base in our calculator to solve it. Okay, let's go ahead and put a log base 10 on both sides. Okay, now that we have a log on both sides, we want to try to isolate x. So I think you can probably see what I'm going to do here. I'm going to take this exponent, and using my third law of logs, I'm going to put this as the coefficient. X log 5. Now our goal is to isolate x, and x times log 5 equals log 40. We only have to isolate x by dividing by log 5. And since this is all base 10, we just go to our calculators and we do log 40, close bracket, divide by log 5, and, whoops, typed it in wrong. I'm going to try that again. Log 40, close bracket, divide by log 5, and we get 2.29. I didn't say where to round it, but 2.3 sounds very reasonable as our value of x. So just checking this out here, 2.29, this x has been moved into the front, and we really are just typing in our calculator after we have x isolated. All right. Now I want you to do the same thing with b, so you can pause and do it yourself before you see me work through it. So hopefully this is what you did. 3x is the exponent. Now I want to isolate x, so I'm going to divide by the 3 as well as the log 4. You can do it in 2 steps, but there's no need. We can do this all at once because the 3 cancels, the log 4 cancels, and this is what we would divide both sides by 3 log 4. I don't want to miss it on the other side. Okay, so if we put this in our calculators, log 55, close the bracket, divide it by. Now I have 2 terms in my denominator, so I'm going to put a bracket 3 times log 4, double bracket close to get my answer here. And now solving in this lesson is so important to enter it correctly in your calculator. So it looks pretty simple, but you know when this log comes up, it comes up with a bracket, so we have to remember to close the bracket. This comes up as a bracket, but because I have a 3 and a log 4, I started out with a bracket, which means I have to close that again. Closing it isn't as critical as when you have this opened denominator opening up as a bracket. So if you don't put the brackets in, you're not going to get this solution. If you do get this solution, then you know you've entered it correctly. .96. So there's the brackets that I'm referring to. You know you've done it right if the answer is .96. Okay, not bad so far. Let's keep going. Now, you know what I did here and I want to do here is to reverse the order here, because this one is pretty tricky. Let's work on one of these D question first. I'll have to remember that the solution for that one is right here. Now, again, the rule is to put a log in front of both sides. Now these look really similar to the ones that we did with exponents, so these are exponential problems. But we can't do these by changing the bases. Just like the last 2 examples we did. We can't find a base that will be the same, so we have no other algebraic way to solve it besides introducing the logs. Nice thing is that you could still do y1, y2 intersect to check your answer. So more than one way to do it makes you feel very confident when you get the same answer for both. Now our exponent this time is a binomial. That's what makes this one a little more interesting. So when I move that exponent to the coefficient position, the front of the log, I need a bracket because it's a binomial. Now I want to distribute the binomial because there's two parts. One of them is the variable that we need to isolate. We have to distribute this. So it looks like minus 1 log 17. So there's the x and there's the negative 1 distributed. There we go. Now we have everything distributed. We have still two values, two parts of each side with x in it. So I need the x terms to be on one side. Doesn't matter which side you choose. If I choose to move this to the left side, I'm going to subtract. So what I have left here is 3 log 12, and this part of the left side, I'm going to move log 17 to the right side by adding it to the right side. There we go. Now we have our x terms on one side, the non-x terms on the other side. When we have two terms with x in it and we need to isolate x, the only alternative here is to factor out the x. So there's a lot of steps here. Nothing too crazy difficult, but a lot of steps. Easy to make a careless mistake. I hope everybody now sees what the last step will be. To get x by itself, I am going to divide by everything that I'm multiplying x by, which is this whole expression. Okay, so this is what x is going to equal. I want everybody to be able to put this in the calculator correctly and get the right answer. Now, being a little conservative, what I often do is type in the numerator 3 log 12 plus log 17 . So I'm closing the bracket, 3 log 12 close bracket plus log 17 close bracket, enter. So that's my numerator. Divide by bracket log 17 close bracket minus log 12 double close bracket, enter. Now I'm getting 29.5, and that's how I've entered it. Let's check. A lot of steps, so I'm going to extend this page so we can, oh, no problem. That's because our solution is on the other side. Oh, good. That was what I was looking for. Okay, so here's the written out steps. Nice and neat, a little bit neater than my work. And without the brackets being shown here, so this is still really important. You have brackets here, and double close. So the numerator I type in first, press enter, and then divide by brackets denominator. So try that and hopefully your answer comes out exactly the same. So the reason why I switched those initial two was because this one is even trickier. So hopefully you have room for this somewhere. I'm going to move it down here and work through it, all these steps. So the reason why this one is a little trickier is because we have a product on the left side. So I'm going to start by introducing a log to both sides. So that's never wrong. Put a log in front of the entire side. Now we have a log of a product. So I'm going to separate this into 2 logs. And that step right there is where I see the most mistakes. Separating a product into 2 separate logs using addition. We're still working with base 10. Now we need to isolate x. We have an x on both left and right side. And this is what it looks like. Same as last time, we have a binomial exponent that gets moved to the front. We need to distribute it. So I'm going to distribute the x and the minus 1. Distribute, or just move the exponent x to the front on the right side. We now need to get the x variables together. So x log 2 stays on the left. X log 5 okay, I think I'm doing this the long way. Instead of minusing x log 5, I'm going to put my x values on the right side. Bear with me here. Instead of moving everything over to the left side, let's just move the x to the right side. Minus x log 2, so what we're left with is log 3 minus log 2. Once we have the x's on one side, we need to factor out. Okay, hopefully you see where we are now to isolate x. Log 3 minus log 2 over log 5 minus log 2. Put that in your calculator. Let's see. I'm going to type in the numerator, log 3, close bracket, minus log 2, close bracket, enter, divide by, bracket, log 5, close bracket, minus log 2, and I get 0.44. And I believe that was the correct answer. Was this the solution that we were? Yeah, this is it. Hard to see anything there. So, if you want to see all of this nice and neat, that's how it looks. Okay, so 0.44. Now let's move on to some more complex log equations. So we talked a little bit about restrictions, and just to remember, every log function, this is your x term, and x is greater than 0. Remember the log graph. Log graph, x is greater than 0. So greater than 0 is this part of the log. This part of the log. Even when there's transformations, these values must be positive. So when we look at this, we have 2 binomials in that position. We have an x plus 1 and an x minus 5. So if x plus 1 has to be greater than 0, that means x has to be greater than negative 1. If x minus 5 has to be greater than 0, that means that x has to be greater than 5. So which is it? Is it both? So it says the first restriction is redundant. If we say x is greater than 5, then the first restriction is redundant, because all values that are greater than 5, hang on, all values that are greater than 5 will be greater than -1. So if you think of it on a number line, it might be helpful. But what we need to do is just see which one covers the other one. For example, if you said just x is greater than -1, then that means x could be negative, or x could be 0. And 0 wouldn't work. It would make this undefined. So it can't be 0, even though 0 is greater than -1. So the only restriction that you would write is this. You wouldn't write both of them because it isn't both of them. It's only the one. All right, now let's look at an equation here. We have a log expression equal to something. But we also have laws of logs that should be applied here. So if we wanted to solve this, what we would do is use our laws of logs and combine to make a single log. All right, because it's addition, we would multiply. I'm not even going to FOIL it out yet. What we need to remember here is every time you have a single log equal to a constant, when you want to solve anything, you're going to flip to exponential. So this is the base 7, exponent is 1, and this is what it equals. So a log equals to a constant, flip to exponential and solve it. So we have a quadratic, not a bad one to factor. Factors a -12 that add to give you -4 would be these, -6 and +2. So now we're saying that these are our two solutions. So here's where the restriction becomes very important. When you have two solutions, any solution, you always need to go back and check your restriction. So remember the restriction, x is greater than 5. -2 is not greater than 5, so our answer is x is 6. Another way is to put both of those back into the original equation and see if it works. You would quickly find out that -2 is not going to work. All right, look at this. Whoa, what is the restriction here? This looks kind of complicated. Restriction on this variable is greater than 0. 5 is not a variable, so no restriction on that log. But now we have 2x squared plus 2. So let's see what we can do with this. 2x squared plus 2. X squared is greater than -1 if we isolate it for the squared. But just use your logic here. X squared is greater than -1. What values of x would work for this? Negative values, if I square them, become positive. So they're all greater than -1. 0 squared is 0. That's greater than -1. There is no values here that would be less than -1. In other words, x is real. X can be anything. There is no restriction for this one. There is no restriction for this one. There is a restriction for this one. So the only restriction that applies in this whole problem is greater than 0. Okay, I'll pull this out just to show you that it confirms what we just talked about. None greater than 0 and greater than 0. So that's the only one that we need to worry about. All right, how are we going to solve this? Again, we have two logs on one side, but not equal to a constant, equal to another log. All right, well, we can still use our laws of logs and combine the two on the left. Okay, let's go down here, and I'm just going to rewrite the problem right here. And because it's subtraction, I'm going to write it like this, plus 2 over 5 equals log x, base 2 of x. Now, nice thing about this one, when you get left side and right side to be a single log, just like when we drop the bases, we can drop the logs here. These are both base 2. That means that this has to equal this. So no more logs, it's just 2x squared plus 2 over 5 has to equal x. This will only work if you have a single log on both sides. Same idea as when we had a single power on both sides and we could drop the base. Single log on both sides, now you can forget about the logs. Let's solve this. I'm timesing both sides by 5. We have a quadratic. Now we need to factor. So if we're doing decomposition, we have two numbers that multiply to give us 4. And add to give us -5. So that means we're going to have -4 and -1. So break it down using decomposition. I'm running out of space here, so I'm going to move all this down. And I'm going to do decomposition because it's been a while since we've done one out. So that's what our two factors look like. This tells me that x is 2 and x is 1/2. Both of those values are greater than 0, so it looks like they should both work, but let's check. If we put 2 in here, that's going to be 2 times 2 squared plus 2. Well, we know this side is going to be 1. Log base 2 of 2 is 1. Log base 2 of two times 4 is 8. 8 plus 2 is 10. I can't evaluate those individually, but I can combine these into a single log. 10 divided by 5 is 2. So that works. Let's see if the other one works. If we put in 1/2, we have log base 2 All right, let's see if this is going to work. Log base 2, and this is going to be 1/2 squared is 1/4. 1/4 times 2 is 1/2. 1/2 plus 2 is 2.5, or 5 over 2. So I ran out of space on the other side of this equation, is log base 2 of 1/2. Well, when I was checking the other one, log base 2 of 2 equals 1. Log base 2 of 1/2, -1. Does this side also equal -1? Log base 2, 5 over 2. So putting these together, I have 5 over 2 divided by 5. Well, divided by 5, that's the same as timesing by 1/5. So these both work. And to check that algebraically is a good idea. And don't forget, there is also the possibility of checking graphically. We could put all of the Left side into y1, right side into y2. Second trace intersect, we should get the same answer. All right, this is important because it's very confusing when you see exponents written in logs. There's so many different ways it can be seen. Really want you to understand what it means. So we know our law of logs with a 3 out front here. That 3 can be moved to here. So these two are equivalent. What might not be very clear is when the 3 is here. That 3 is actually the same as cubing the whole log. So this is a log of 100 cubed. That reminds me back to trig when you have tan squared or tan x squared. It's always, the exponent is written right beside the trig ratio. Well, that's the same as logs. This is log 100 cubed. So these are equal. The entire log cubed would be a 3 right here. Whoops. Okay, that becomes important when we do a problem like this. So log x squared plus 3 log x minus 4. Look at that problem. Log x squared plus 3 log x minus 4. That looks like a trinomial that we can factor with a replacement variable. If we replace the log x, get it out of there, I am trying to be neat. I know sometimes hard to tell. A squared plus 3a minus 4. Wow, look at that. How is that not an easy quadratic for you to factor? So just so you have it in your notes, I'll show you what those say. That log exponent 2 of x is the same as the whole log squared, not the same as 2 log x. Okay, so what are we going to do with this quadratic? We're going to factor it. Correctly. So there's our two values for a. We have a positive 1, negative 4. Well, that's not x. We need to solve for x. So let's go back to what we replaced a with. Log x equals negative 4. When that log in the original equation, there's no subscript. That's base 10. Those are base 10 logs. So when we go to evaluate for x, it's switching to exponential. So log base x equals negative 4 is the same as the base is 10, the exponent is negative 4. What it equals is x. Log base 10 of x equals 1. 10 is the base, 1 is the exponent. Those are going to be our two answers. So you can write 10 to the negative 4 as a decimal, or just leave it. And x is 10 is the second answer. Okay, let's see what we have here to confirm. And using a b value, it's exactly the same. When you see that quadratic, after you replace the log x, it becomes so much easier. All right, so this looks like it was cut off slightly. Oh, it's not just the way it is. It's not just its position. It has been cut off. So what is 10 to the negative 4 is the same as 1 over 10 to the 4. 1 over 10,000. 1 0, missing. And this is, the other one is just x to the 10. What about restrictions here? Are both these values correct? So we know that these are our two answers. Let's check our restrictions. Look at our restrictions. Where's the value here, here? It's just x. So our restrictions are pretty simple in this one. X is greater than 0. X is greater than 0. Both of our answers, even though 10 to the negative 4 is very small, it is greater than 0. So these are both possible solutions. We could do an algebraic check to verify, or we could do a graphic check to verify. All right, now looking at these problems, hopefully you're getting confident with those formulas for growth decay. NT would look like this. So it says an agar plate has 20,000 bacteria. A scientist adds a serum that causes it to decrease by 40% every 3 hours. All right, see if you can fill that in without my help, and then watch and work through the solution, see if it matches mine. How long will it take to have 300 bacteria remaining? So a lot of keywords there that should help you fill these values in. 300 remaining is the number after a given time. 20,000 initial amount decreases by 40%. 1 minus 0.4 is 0.6, so that's how much remains. And it says every 3 hours, which is the amount of time it takes to decrease by that, and that is the D value. So T over 3, and remembering the units. We're in hours, so T must also be in hours. Now, when it says how long will it take, that's an indication that we're looking for T. All right, this looks kind of confusing. Should we put a log in front right away, or should we simplify a little bit? So on your quiz, you had something similar. You did y1, y2 intersect. We can do that again. That'll give you your answer, but you'll be asked to solve one of these algebraically. To make it a little easier, what I usually do is divide the NT and the NO. So I'm going to go 300 divided by 20,000. And I'm getting 0.015. When I put a log in front, then I don't have to worry about separating it into more than one log on the right side. I like working with it this way. Log of both sides, move the exponent to the front. And we want to isolate T, so we can do this in 2 steps, or 1. You could see that we need to divide by log 0.6, and that will cancel here. So we have T over 3 equals, I guess we could calculate this now, or times it by 3. So I'm going to calculate it and then times it by 3. Log 0.015, close bracket, divided by log 0.6, 8.22. I'm not going to round it. I'm going to times it by 3, 24.66. So we're looking at pretty much one day. We have 24.66 hours, 24.7 hours for it to reduce to 300. So let's look at the solution that's worked out here. So 24.7, it's been rounded to 1 decimal place. I'll move this so you can see the whole solution. And yes, this method is the same as what I did. I divided by 20,000 and then put in the log on each side. So these word problems should always be finished with a sentence and with the appropriate units of measure, hours. Okay, this one looks similar. Again, we have growth decay. So a culture estimated the number of E. coli in a culture to be 1,000 after 90 minutes. time elapsed. The estimated count is 19 to be 1,000 after 90 minutes. The estimated count is 19,500. Determine the doubling period to the nearest minute. So the originally estimated number was 1,000. After 90 minutes, the count is 19,500. So it's increased a lot after 90 minutes. So NT there's a keyword for your base. We're looking for the doubling period. So we're looking for the denominator, the doubling period. 90 minutes is the time elapsed. So the unit we're working here with is minutes. And we're given NT and NO. So you work through this, and then you can see how I've worked through it. But I know you guys can do this entire question yourself. So the initial is 1,000. 19,500. Doubling. T over D. Well, these numbers look similar to the quiz question that we did. Now again, to solve it algebraically, we're going to use logs, but I would divide by the 1,000. So dividing by 1,000, we get 19.5. And on this side, we get 2 to the 90 over D. Now we can put the logs in place. Move the exponent to the front. Now when the denominator is the unknown, I think what I'll do here is divide by the log. See, that is log 2. I really didn't need a bracket there because it's throwing me off, but let's put this in the calculator. And log 19.5, close bracket, divided by log 2, close bracket. So what I'm getting here is this. Now I'm afraid I would lose a lot of people here because the denominator is the unknown. We did have a denominator in the unknown on the quiz, and most of you handled it well. You multiply both sides by D. And then in order to isolate D, what we end up doing is taking 90 and dividing it by this number. 4.285, and try to be as accurate and not round it until the end. So I'm going to go 90 divided by the answer, 21.0. And again, what units? Minutes. .0 minutes. And I'm going to confirm 21 minutes. Whoop, let's pull that way down here so we have some more space. This is what it would look like a lot neater. And that confirms the 21 minutes. All right, do your homework. There is a good tip. So you got to get really serious about getting your assignment complete, work on the handout with extra practice, and we'll have some time in class to go over some of those harder, challenging questions.